Hi and welcome to a little hacking and modding and repurposing video, or at least attempting to do so. Thing is, I ordered a large bin of surplus stuff from a store a while ago, and now I came to actually looking at it, and one of the things which like are not worth anything anymore today, or at least look like it, was this. It's a mobile phone charger for the car, but for old Siemens phones. Oh, not Siemens, sorry, Samsung. Old Samsung phones, E810, E720, stuff like this. You see the nice old kind of drawing. Yeah, those were the days. Looks like 2002 or something like this. And it looks like this, and yeah, it looks like a perfectly fine type of charger, which could probably be repurposed in some way. I mean, we don't need this kind of connector anymore today. Nobody's got these phones, but maybe we can convert it to an USB charger. It would be better than just throwing it away. So, of course, the first thing we're going to do is taking a look inside this thing. I'm going to start with the connector actually, because it looks like there is some kind of LED or something in there, which you can see here. So I don't know, probably there is a bit more than just a connector and a piece of wire. We'll see. Luckily there are just two screws, nothing too hard to open at all. So we can probably just pop this lid off with a bit of force. And nope. I'm stumped. There are like these small clap kind of things, you know, to... Okay, no wonder I don't get this open. There we go. What is this? Okay, I have to admit I lied to you. I already had this thing open before, which was, I mean, I had a bit of a go at this before I realized that it could make an interesting video, and yeah, I was a bit too forceful at one point, so I ripped this thing off totally, including the copper pads on the PCB. So yeah, this is why it looks like this. Yeah, just two cables from the actual power supply. Tiny little PCB we have here with a huge LED on it, directly having these metal connectors going into the plastic, and it's holding pretty tight. I'm going to leave it in there. Now the thing is, at first when I saw this thing, I thought, wow, there's actually some stuff in there. What is it doing there? And I thought, man, okay, maybe it's some kind of, I don't know, ID mechanism for detecting the kind of phone, because it says it's supporting multiple phones. And well, I would have thought that they just all use the same voltage or something, but I thought, who knows, maybe, I don't know, maybe it's like with the modern chargers of some phones, that it can detect what is needed by the phone and supply the right voltage. I don't know. And when I powered this up, all that happened is that for a brief moment it flashed red, but nothing else happened, and I wasn't able to measure any voltages over there, or I don't know, nothing really. And I tried, and first I thought, okay, so that maybe it's sensing the type of device by having resistances across there or something, and I shorted some of these pins. Nothing happened with the LED at all. And I thought, who knows, maybe it's broken, or maybe I don't know, I need an actual phone for it. So, but now I looked up this little chip over here, and it's quite interesting. I was a bit surprised when I found out what it was, because I didn't expect that actually. It's a lithium-ion, lithium polymer battery charger. So here we have the datasheet on my computer. Excuse me for this crude method of doing a screencast. So basically the chip on here, as I said before, is a one chip solution for a lithium ion lithium polymer battery charger. Basically it does everything you need for a charger, and we can probably also find in this sheet the sample circuit, the typical application. And yeah, sure enough, there it is. We can also see that the green and red LED over here are also a feature of this chip already. I mean the control of these LEDs. And this is basically just the big LED we saw here, but it's a dual color LED on this board and not two separate ones. Anyway, what I'm most interested in is this reference resistor, or actually the resistor for setting the reference current, because the reference charge current will give me a hint on how much current this thing is going to use from the power supply normally, which then allows me to estimate how much current we can use for our USB. And there, I'm sure there is a formula somewhere for there we go. Okay, I know you can't really see it because of the light condition, but there is a resistor on this board actually, which is connected to this RF pin, and the value is 100 kilo ohms. So 100,000 ohms, which is exactly 10 times 5. So this makes it very easy because our resistor is 10 times 5 and the whole thing is multiplied by 10 times 5, so these cancel each other out, and what's left is the 0.8 volts, which for us now means not 0.8 amps. So apparently this charger was designed to charge the battery with 800 milliamps to 4.2 volts. So since the power supply originally gives us 4.6 volts, it's safe to assume that we can take around 500 milliamps out of this thing for USB at 5 volts. So yeah, looks like those old Samsung phones didn't have the charging circuit in the phone like they would today, but actually in the charger. And probably, I mean, you can see that this connector called P1 over there isn't connected to anywhere at all. So I guess the remaining 3 pins are like plus, minus, and temperature detection on your battery, on your classic lithium-ion battery. And this is directly the charging circuit, so you could actually directly probably access the battery terminals from your connector down at the bottom of the Samsung phone. Okay, so I was curious about the voltage this thing actually outputs. So yeah, let's see. Maybe it's 5 volts and we don't need to do anything except for bodging on a USB connector or something. So I've got the power supply here, and usually this, I mean, I didn't say it, but I thought it's clear that this goes in the car, into this cigarette lighter in the car. So, and they usually have center positive, like all sane DC plugs also do. I mean, there are some of these insane center negative and you don't know it and it blows up your device, but not in the car. Usually they have center positive. So I'm going to put the negative here, positive over here, and yeah, let's power this up and see the voltage over there. Yeah, I've set my power supply to 12 volts, of course. So let's turn it on. Yeah, 4.6 volts. That's quite low for USB. So unfortunately we can't just put the USB connector and call it a day, because yeah, I don't know. Depending on what device it is, it might work, or it might kinda pretend to charge but not actually charge, or it might just fail. Anyway, it's not valid voltage for USB output. So we have to tweak this thing a bit. Okay, so we can remove, of course, here the tip. It looks like it's screwed on, and because there are no other visible screws or anything on this thing. Okay, so what we have in here is a fuse. There we go, 1 amp, 250 volts. Okay, so I guess we can just squeeze this thing open, but I don't want to crack anything, so I'm just going to go in there with the screwdriver carefully, and yeah, that sounds right. Pop this thing open. Okay, there we go. Yeah, oh yeah, well, I forgot that there is a little sticker on it. Charger compatible for use with Samsung E810. I have no idea how old this phone actually is. Input 11 to 30 volts DC. Warranty void if removed. Yeah, of course. As if I need the warranty on this thing. This is actually the downside of a board, apparently. And yeah, again, I lied to you. I had this open as well before, and this is why this looks a bit scratchy over here. Yeah, that's because it was like it was with this melted plastic. I don't know the word in English actually, which holds the board in, and I had scraped it off so I could get the board out. So let's do this again. It's not that easy. Okay, there we go. So what do we have here? It looks like a switch mode power supply of some sort, with the big inductor over here. Actually a second one, a smaller one in there. Some passive, some caps. Yeah, actually some unpopulated stuff here down here as well. What's going to be interesting, of course, is what this chip actually is. Maybe we can find something. We can see here it's an X34063 E10A. Okay, I'm going to Google this. There we go. It's an monolithic control circuit containing the primary functions required for DC to DC converters. Exactly what we expect to find in here, because this is basically a DC to DC converter from 12 volt or according to the label 11 to 30, step down to 4.6 volts. And if we have a look on here, the characteristics: operation from 3 to 40 volt input, short circuit current limiting, and so on and so on. What we're interested in is actually the way this thing is used and the formulas used to calculate the output voltage. To this data sheet again on my computer from Excellent Semiconductor. Sounds excellent. Yeah, basically it's again a one chip solution, this time for a switch mode DC to DC converter, and yeah, it can be a step up, step down, or inverting switching regulator. In this case, of course, it's step down from between 11 and 30 volts down to 4.6 volts. We can see here the pin configuration, and this already looks interesting. Comparator inverting input. So this is probably what we need to look at, because the way these things works basically is there is a comparator inside and a voltage reference. Yeah, there we have a block diagram. Okay, so here is a comparator, and it's comparing basically this 1.25 volts internal volt reference against whatever we are feeding in here, and this is used to regulate the output voltage. So what we need to do here is we're feeding it something which we expect to be 1.25 volts, assuming that the output voltage is the value we want. So basically we're using a voltage divider, a resistor voltage divider of some kind. Let's say we want 5 volts, then we would need to split it in 1 to 3, so that we are feeding a quarter of the output voltage back in here, which of course 5 divided by 4 is 1.25. We would then expect it to be 1.25 at this point, which this comparator will ensure that it is. And in order to do so, it's driving, it's switching this oscillator on and off, which is then later driving some current into an inductor, and yeah, at the end we're getting our output voltage. So the question is how this is configured exactly. I mean, basically we already know how it's done, but I'm sure there is also a formula somewhere. And there's our formula. It makes sense now, similar to what I said. Okay, so here I found the step-down converter example application, which again looks a lot like what we see in our circuit. A large inductor here with 220 microhenry, which is probably like the big toroidal one we saw before, and a smaller one with 1 microhenry. And well, this one is probably the one which actually ensures that we get the right voltage and it keeps at this level, and this one is just filtering. Actually, I have to say, it looks like this device, it looks complicated for a charger, but actually it's very simple in a way that it looks like they just thought, how can we get this kind of charger? The simplest way, well, we need 2 ICs, one as a power supply for the DC to DC converter, and one for actually charging the battery. We just like get some one-chip solutions for each, put the same circuit around it they use in their datasheets with the small modifications, and yeah, working. What else is needed? And they didn't even put all the components into the power supply board. They probably had some better filtering or stuff, but then they figured they don't need it because the charger IC handles the ripple current quite well. Yeah, whatever. So what we are interested in are these 2 resistors, R1 and R2. R1 going to ground and R2 going to the voltage output. And by modifying these, we can modify the actual output voltage. Oops, a little correction. Before I looked at the wrong circuit, the voltage inverter instead of the step down, where a few things are different. One of them is that pin 4 is not wired to ground, but instead to V out. This is not true here, so the pin 4 you see on the paper is wrong. It's not pin 4 because pin 4 is just ground. It's actually just V out, which then goes to the inductor and stuff. So this is basically how it looks. R1 and R2, and again the output voltage formula. So we need to look for those 2 resistors, and hopefully it makes sense if we apply them to this formula, and hopefully the number makes sense, and then it means we can probably modify these resistors and therefore modify our output voltage. So in order to find these, we need to trace the things a bit on here. Pin 5 is this one over here, so we need to see what is connected to pin 5, and hopefully we find 2 resistors, one connected to ground, one connected to V out, and these are our R1 and R2. And when I say R1 and R2, I don't mean those component designators written here like R8, R10. I mean the R1 and R2 from the schematic on the datasheet. So if we turn this around, we can see again that this is our pin 5. And from there we go here, and actually on the other side we see that this is just a piece of wire over there It's not a real resistor, even though it's labeled R1. And it looks like they did this multiple times on this board here as well. Probably they'll kind of simplify the circuit a bit after design in order to save some money. Anyway, if we follow this fake R1 in quote marks over here, basically what we get is over there, which is now connected both to here and to down here. And this one is actually the resistor right next to the fake resistor on the other side, which goes there, and the other end of it is ground. So this obviously is our R1 here, so we just need to follow the trace in the other direction to find our R2 over here. So if we have a look at this thing we now calling R1, it's a bit hard to see on camera, but it's actually a 1.1K resistor. Back to looking for our R2. Here was the junction which went off to our R1, which was this one here. So following this one down here, we land at this point, which again is just a wire connecting from here to down here. We can see that right next to it there is again a fake resistor R9 over here, another piece of wire, and actually these two are connected because the first longer wire we saw went from here down there, which is now directly connected to here, to the other resistor, and yeah, to this unpopulated component down here, which I don't care about. Same for this not populated transistor over here. So it goes there, and this is exactly the small fake R9 we saw on the other side. So it just connects from here through here through here, which then below this wire goes down here and basically connects to these two resistors, as we will see on the other side, because these, which are then connected to here and then to the red wire, which is the voltage output, bingo, we can see that these are these two resistors over here in parallel. And if we look closely enough, this one is a 3.3K and this is actually a 21K. And all these resistors apparently are supposed to have 1% tolerance, if I'm reading this correctly. So these two parallel, I'm now going to call them R2A and R2B, make together our R2. So basically now we have two resistors in parallel making our R2, which if we calculate the total resistance, it makes a 2.9K basically resistor out of these. And if we now botch these two values, 1.1K and 2.8519K into the equation, we're getting 4.49 volts. And yeah, I know we measured 4.6 and not 4.5, but I mean, I know it's supposed to be 1% tolerance on these resistors, what I saw, so it wouldn't account for an error like this, which is, yeah, a bit more than a bit more than 1%. It's actually 2.5% error we see here about that. But maybe, I don't know, maybe it's a combination of the tolerances, all a bit away from the actual nominal value, or maybe there are some other components playing a role in this. Anyway, it looks pretty close to the 4.6 volts we measured, so I think it's safe to assume that these are actually the resistors we need to look for, and we can change them to adjust the voltage. Basically what I want to do is to play a bit with the R1 value, because it looks like if we are reducing this value, we are able to increase our output voltage a bit, which is exactly what we want, because we want to change it from 4.6 to 5. I mean, of course we could also, we could also increase R2 but increasing a resistor and testing it is a bit harder because you actually need to separate a connection somewhere and put more resistance into it. But decreasing is easier because I just need to put another resistance across it in parallel in order to reduce this value. So this is what I'm going to do. I have those 1.1K currently as R1, and I'm going to put another resistor in parallel. I'm going to start with the pot so I can adjust it and see what is the output. Okay, so what I've done here now is I hook the thing back up to my 12 volts, but I also here hook, oops, there we go. I also hooked some wires up here, basically across the resistor we saw before, the 1.1K resistor over here. It's a bit hard to see right now with the light, but anyway, I hooked it to the fake resistor and to the top of this resistor, which basically is just across it. So now we can put another resistor in parallel to this one by using a pot like this. I now, oops, something happened. Oh yeah, well, this happened. My multimeter was detached. Okay, now we are back in business. Okay, so now I can turn this pot here to basically adjust my additional resistor I'm putting across R1. So let's turn this thing. Yeah, it appears to work. We are going up. Whoa. Okay, now something weird happened. We went up too far and there we went. Let's see if I can do this again. Boom, 0, boom, 8 volts. And what you don't see on my power supply, normally it says 0.00 amps because there is no real load on this thing. It's like below 1 or no, below 10 milliamps. But if I ramp this up too far so that this thing happens, boom, then suddenly we're getting 250 amps on there. Anyway, the thing we want is 5 volts exactly, which is a bit touchy on this pot. I don't even know what is the value of this pot, but I have to be very careful. No, not that far. Yep, there we go. 5. Oh, please. Yeah, no. But that's good enough. Now all I have to do is measure the current value of this resistor, of this pot actually, but the current resistance we have across here. Whoa, okay, not, yeah, touching those, of course, plays with the voltage quite a lot. Yeah, but you get the idea. So, and trying to get the same kind of resistor actually into the circuit, or if nothing else is possible, then maybe a small trimmer and adjust it, but a fixed resistor would be better. Let's try, let's go and measure it. So as we can see on my other meter here, it's 9.06 something kilo ohms. 1K and 10K in parallel, that's good enough. 9.09 kilo ohms. So what we're gonna do here is make our circuit look like this. So this is the original 1.1K resistor, and we're going to put a 10K and a 100K in parallel. So at the end, yeah, I didn't write it quite well here, but basically our R1 total value is now going to be about 981 ohms. R2 of course stays the same. Putting this in the equation now gives us 4.88 volts as opposed to the 4.49 from before. And we already noticed that we measured 4.6 even though it says 4.49 here, and here we're measuring 5 even though it says 4.88 here. So maybe, I don't know, maybe the voltage reference is off or something, but we measured it that it's now going to be 5 volts. I just wanted to demonstrate that the difference between the old and the new value makes sense. I just realized that while it would certainly work this way with 3 parallel resistors, and it was a nice way to test it, of course, with the pot, it's probably easier, and also it would look a bit less messy if we would just replace this R1 by another resistor. And looking at the value we get from those 3 parallel resistors, 982 ohms, I mean, I think I just need to check some of my 1K resistors to find anyone that far away from the nominal 1K that it's the 982K or 981K I'm looking for. I'm sure I'm going to find one like this. And yep, there we go, 1K, but actually 983, that's gonna do it. Now there we have this thing, the 1.1K resistor, but before I'm now going to put the other resistor in, I'm going to measure this thing out of circuit and verify that it's really 1.1K, and if not, what is the real value, and recalculate the other values based on it. 1098 ohms, that's close enough. So this means I don't need to modify anything in my calculations, and this not really 1K but actually 983 ohms resistor will do just fine. Okay, so now I put my other resistor in, and I'm just going to solder it, and then it should work perfectly. Let's see. Okay, now the moment of truth. The new resistor is in here. Let's see if we get the 5 volts we want or not. And there we have it, 4.998. That's close enough to 5 volts. We can put a USB connector on here and it's going to be just fine. Okay, well, I decided to take a look on the scope for a second if this output signal is actually smooth enough, and no, it's not really. Take a look at this. It's a 20 millivolts per division, and yeah, we have like 1, 2, 2.5 divisions, like 50 millivolts like noise on here. Or yeah, it's not noise. It's a bit, yeah, it's just a bit oscillating over here. You can see it's ramping up and then trying to find the right spot and then up again. Yeah, it's no good at all like this. So I'm just going to add a little electrolytic cap at the end, 100 microfarad. Ah, yeah, that's already a lot better. That's now at 10 millivolts per division, and it's negligible. Actually, if you look at the board here, you can see there is a space for a cap in here, together with some other components, and it's just unpopulated. So they were saving a few cents on this thing, probably because the charging circuit, on the other hand, didn't really need a stable voltage or something like this. There we go, I found an old radial electrolytic cap with 100 microfarad and just bodged it in there. It's not supposed to go there. I know there is a C5 marked over here, but I don't know, it's something else. It's not directly across the output, but yeah, I just put this one in here and it works nicely. So let's go and try this thing with an actual USB device. I would like to charge my phone with it, So I'm now going to connect the output to an actual USB socket. This should be ground. Careful not to short anything. And this should be V in. Looks okay. So first I'm going to plug this USB power meter in here. 4.97 volts. Well, it's a bit off, but doesn't matter. And okay, so I'm now going to check charging my phone with this thing. So let's plug this thing in, and yep, it's charging. However, I'm not totally sure why it draws only 0.14 amps here. I should draw half an amp or something like this, and the voltage dropped a bit. That could be due to the resistance in this pretty long lead we've got on this thing. And it actually looks like this could be the case, because measuring the voltage again directly at the output of the DC to DC converter, we are getting 5.93. Well, it dropped a little bit, but here it says 4.62. And no, it's not the USB power measurement device which is lying. When I'm measuring it directly at my USB socket, I'm also getting only 4.64 volts. Oh. You know, my original idea was leaving the board in there like this, like it was originally, and just in the end connector here making some room for putting a USB connector in there like this, and gluing it shut and leaving the cable on it, so you have a car charger with a flexible cable, and at the end a USB port, and from there you can charge your stuff. But now it looks like the cable is not such a good idea, so my new plan will be removing this cable, instead using this space in here, this cutout edge, to fit a USB connector, something like this, and again gluing this thing shut. Well, a little issue with this cap, I didn't realize that the mounting hole is right below this, so yeah, now I just cut it a bit. This should do it. Perfect. And I'm now going to try a bit of a crude method to hold this thing in place, because you can see I bent this connector holder a bit, because I want to fit it in here and just solder this onto this ground pin here, which should be fine to put the case on ground, and this should just prevent it from flapping around. Well, this is probably the crappiest solder joint ever, but it's because I had to connect the ground plate to one lead of this capacitor we put here before, because it's not directly connected to ground by default, but to another unconnected component, so I just bridged those. And yeah, you're right, I said I connect this one to ground, and this is indeed ground, so I could have just connected these two over here, but the reason I didn't want to do this is because I didn't want to melt this solder joint again and maybe loosen my USB connector over here, and then yeah, it would have become quite messy this way. So I chose to connect it to the original connections where the black and red wire originally went off from. So does it work now? Yes, it does, and look at that. It dropped again a little bit, well, more than a little bit, but now my phone is drawing 550 milliamps, as I would expect from a USB port which doesn't say anything else. You know, by say I mean if we connect the D plus and D minus, the data lines, in specific ways using resistor voltage dividers, we can signal compliant phones like the iPhone that the USB connector, that the USB charger is able to provide greater currents like 1 amp, 2 amps or something. But without this, around 500 milliamps is exactly what we expect. So now it seems to work a lot better. I'm still not sure why the voltage drops that much, but it appears to be fine for the charging purposes of my phone, and nothing should draw more than 500 milliamps here anyway. So yeah, looks like we did it. Look at the lightning bolt, it's the look of victory. And how much current is it drawing from the 12 volt supply at half an amp charging current? 300 milliamps. And measuring the output voltage under load with the multimeter instead of the USB tester gives us 4.8 volts. So let's try and get the efficiency of this. We have 12 volts input drawing 300 milliamps, gives us 4.8 watts, and on the output we are seeing 4.8 volts drawing 550 milliamps. That makes 2.64 watts. So dividing these two we get 0.55, which means 55% efficiency. That's of course not a very good value, but fair enough for a little hack like this. Okay, I left it running a while with my 500 milliamps mobile phone load on it, and checking the temperature of the chip, 45 degrees, looks fine. So all that's left now is figuring out how to fit this thing in here. Well, that's not hard. Time for my Dremel. Yeah. Now to the other side. So I'm now gluing this thing in with some black hot glue I had lying around, and this should also make up for all the dirty kind of edges I put in there now. But first I'm putting a bit of glue in here. This should make sure that the connector is not just breaking off next time I'm plugging something in here. And now I'm just gluing this whole thing down here a bit, so that it's not going to be ruined just by plugging something in or out a bit too harsh. I'm putting the top cover back on. Yep. And some final fixes in here, just to make up for the shitty hole I put in there. Yeah, I know it still looks a bit awful, but I have to admit I'm just not that good at all the mechanical parts of this. Anyway, all we need to do now is put our fuse back in and screw the top on. There we go. We can now put our own little sticker onto it if we want to. Yeah, smeared a bit, but it's supposed to say 12 volts, 0.3 amps DC in, 5 volts, 0.55 amps DC out USB. So let's do a final test now that everything is back assembled. Hook it up to 12 volts again, and sure enough the LED comes on. Yep, working nicely. Phone is charging again. Perfect. So that's it with my old Samsung car charger to USB mod video. It's the first of this kind I did, so I hope it's at least a bit interesting, and yeah, I hope you enjoyed watching it. Maybe there will be a next one. Bye.